Greetings. Today we will be looking at the physical properties of driven harmonic oscillators. First, we will give a brief introduction to driven harmonic oscillators, and then we will give various examples of different driving forces. Firstly, the constant driving force, then the polynomial driving force, then the sinusoidal driving force, and then the exponential sinusoidal driving force. Afterwards, we will return to the sinusoidal driving force and look at the phenomena of resonance. And then we will look at the principle of superposition and the Fourier series, and we will use the Fourier series to solve ordinary differential equations. And finally, we will look at the effect of impulse forces on the driven harmonic oscillator. First, let us give a brief introduction to the driven harmonic oscillator. In the previous lecture, we looked at the damped harmonic oscillator, and it has the equation of the following form. Notice that this is a linear, homogeneous second-order differential equation. However, the driven harmonic oscillators are simply the damped harmonic oscillators with an external applied force, and from this, the equation will no longer be homogeneous. As a result, we would need different methods to solve these non-homogeneous differential equations. Now we will look at the general form of the driven harmonic oscillator. The equation of motion is as follows, where the f of t is the force as a function of time, and the general solution is as follows, where x sub c is the complementary solution, and is simply the solution for when f of t is equal to 0. This solution will take exactly the same form as the damped harmonic oscillator, and the particular solution, x sub p, is when f of t is not equal to 0. Since we have solved the complementary solution in the previous lecture, we will only focus on solving the particular solution in this lecture. The simplest case of the driven harmonic oscillator is the constant driving force. If we let the damped harmonic oscillator be equal to some arbitrary constant c, to solve the particular solution, we set c to be equal to the variable with the lowest order time derivative. In this case, that would be x. As from this, one may notice that anything with a time derivative that is higher than x will be equal to 0. And thus, the particular solution will be the following. Now, we will look at a more complicated example, namely the polynomial driving force. If one considers the case where the driving force is a polynomial, where a sub n is some coefficient, then the ansatz is also a polynomial with the same degree, where c sub n is some different coefficient. We will illustrate this with the following example. If we let the right-hand side be some quadratic term of time, where f of f1, f2, f3 are coefficients, then the ansatz is the following, where c1, c2, and c3 are different coefficients. Taking the first time derivative, we obtain a linear equation in time, and taking the second time derivative, we obtain a constant. Plugging this back into the differential equation, we yield the following, and using algebra, we can solve for c1, c2, and c3. Substituting these back into the to x of p, we yield the following, and thus we have solved the equation for the polynomial driving force. Now we will look at a more complicated example, namely the sinusoidal driving force. If we consider the following driven harmonic oscillator with a sinusoidal driving force, where f naught is the amplitude of the oscillation, and omega is the driving frequency, we can actually use a method called undetermined coefficients to solve this equation. However, I believe that using complex numbers is much easier. Using Euler's formula, we may manipulate the equation above to a form with an exponent in it. And from this, we can use the following ansatz. We must state that we're taking the real part of e to the I omega t, which is the same as cosine omega t. And from this, we can use the following ansatz, where x sub p is equal to d e to the I omega t minus phi, where d is some amplitude and phi is some phase angle. Substituting this back into the ansatz, we yield the following. Substituting this ansatz back into the second order differential equation, we obtain the following. And if we set this, the left-hand side of this equation to be dr e to the I theta, then r is equivalent to the square root of the frequencies. Well, it's just, sorry, r is simply the magnitude on the Argand diagram, and theta is simply the angle on the Argand diagram. If this is hard to remember, just remember that it is the square root, is this the sum, so, okay, let's say it is the square root of the sum of the squares of the real and imaginary part, and the angle is simply the arctan of the imaginary part divided by the real part. And from this one finds that d is equivalent to the amplitude of the driving force divided by the magnitude on the Argand diagram, and the particular solution is as follows. Note that this equation has no free parameters, as d and phi depend on the system parameters and the driving force. Now we will look at a more complicated example, namely the exponential sinusoidal driving force. Consider the following exponential sinusoidal driving force. We may use a similar method to that of the sinusoidal driving force. However, since there is a sine function, we would need to take the imaginary part. And for this differential equation, we may use the similar ansatz to that of the sinusoidal driving force to solve this equation. However, we will instead use the ansatz for the simple harmonic oscillator. Doing this and substituting this into the differential equation, one obtains the following. And note that lambda t is the only thing on the left-hand side raised to an exponent, and the only thing raised to an exponent on the right-hand side is I omega minus alpha t. Hence, we can deduce that lambda is equivalent to I omega minus alpha, and substituting this back into the equation, we solve for a, which will be defined in the next slide, but d in this case is the following. It would be f naught over this expression. And writing d as equal to a e to the minus I phi, one obtains the following equation. And note that the amplitude here is similar to that of the sinusoidal driving force, where it is the amplitude of the driving force divided by the magnitude of the Argand diagram. And the phase angle is simply the angle on the Argand diagram. And hence the particular solution is as follows. Now, we will go back to the sinusoidal driving force and look at the phenomena of resonance. First, we will look at amplitude resonance. Note that the equation for the amplitude of the general solution of the sinusoidal force is as follows, and this is a function of the driving frequency. To determine the resonant frequency, omega sub r, one must solve for the frequency for when the amplitude is at a maxima, and hence we must take the derivative of the amplitude with respect to the frequency and set that to 0. And solving for this, we obtain the following. And plotting this equation on a graph, we see that this is true. And now we will look at the kinetic energy resonance. The expression for the kinetic energy is as follows. Note that from your high school physics class, you know that the kinetic energy is equal to a half mv squared. In this case, the v squared term is just the square of the particular solution of the sinusoidal driving force with one time derivative in it. And now, to find the kinetic energy resonance, we must take the average kinetic energy. And to do this, we will take the time average and integrate from 2 pi over omega of t, and then divide by 2 pi over omega. And evaluating this integral, we obtain the following. And to find the kinetic energy resonance, one would need to determine the frequency at which the kinetic energy is at a maxima. Hence, we take the derivative of the kinetic energy with respect to the frequency and set that to 0. And solving for omega sub e, and we obtain two solutions. But we are only interested in the positive solution, as this is the only one with physical significance. From the equation above, one may note that omega sub e does not equal to omega sub r. This is because the amplitude resonance represents the resonance for the potential energy. And when potential energy is at a maxima, kinetic energy is at a minima, and vice versa. Now, we will look at the principle of superposition and the Fourier series. Given that linear operators have the distributive property, where L is some arbitrary linear operator, the principle of superposition allows for the sum of different complementary solutions when the driving force consists of the sum of arbitrary functions of time. From this, the driving force can take the form of any wave if the wave can be resolved by the Fourier series, and this is the Fourier series, where a naught over 2 is the constant term, and there is the sum to infinity of the cosine and sine terms, where a sub n is equal to some cosine function and b sub n is equal to some sine function. The reason for this is if this a sub n was a sine function, this would be equal to 0, and if this b sub n is some cosine function, this would be equal to 0. So, this property is called orthogonality and can be proven by the product to sum rule. And if we let the Fourier series be the driving force in the driven harmonic oscillator, we obtain the following. Then the particular solution is a superposition of the individual solutions, and where x sub 0 of t corresponds to the solution with a naught over 2, and note that x sub n of c and x sub n of s are solutions that correspond to the cosine and sine functions respectively, and do not represent x sub n to some power. Hence, the individual equations for the particular solutions are as follows. Note that this takes a similar form of the constant driving force, and these two take the similar form of the sinusoidal driving force, and thus the particular solutions for the individual equations are as follows. And taking the sum of these would be the particular solution to the driven harmonic oscillator for a Fourier series. Note that a sub n of c and a sub n of s are the amplitudes for the cosine and sine solutions respectively, and phi sub n of c and phi sub n of s are the phase angles for the cosine and sine solutions respectively. It is important to note that there are an n number of solutions dependent on how many terms there are in the Fourier series. And now, we will look at the effect of impulse forces on the driven harmonic oscillators. In the previous few sections, we mainly focused on steady-state oscillations. For many types of physical systems, the transient effects are quite important. Here, we will focus on the transient behavior of linear oscillations subjected to a driving force that acts discontinuously. In this section, we will focus on the two types of functions, the first of which is the step function, and the second of which is an impulse function. The step function, or heaviside function, denoted by h, is given by the following expression. This is known as a piecewise function, where h of t is equal to 0 at t less than t naught, and a at t greater than t naught, where a is a constant that represents the acceleration, and t naught is a time for which the force is applied. On the other hand, the impulse function is the positive step function applied at a time t equals t naught, followed by a negative step function t at t equals t sub 1. This is also a piecewise function and is 0 at t less than t sub naught, and a at between t sub naught and t sub 1, and 0 at t greater than t sub 1. Plotting such function, we yield on the left side the heaviside function, and on the right side the impulse function. For step functions, the equations that describe the motion of oscillators are the following, where note that this equation is only for when t is greater than t sub naught. And considering the initial conditions, x of t sub naught is equal to 0 and x dot of t sub naught is equal to 0, one finds that the particular solution to this equation to be similar to that of the constant driving force. And applying the initial condition the full solution for t greater than t sub naught is as follows. And for x of t equal to the particular solution will be 0 at t less than t sub naught. And then when we use this omega sub 1, this is defined to be the square root of omega naught squared minus beta squared. If one considers the impulse function as the difference amongst the two step functions separated by some time tau equal to t1 minus t0, then the general solution for t greater than t0 is given by the superposition of the solution for the individual step functions. If we let the solution of the Heaviside function to be the following, x sub h, then the solution for the impulse function x sub I is the following. It would be the sum of the Heaviside function at t plus the sum of the Heaviside function at t minus tau. If one allows the duration of tau of the impulse function to approach 0, the response will become vanishingly small. However, if one allows a to approach infinity as tau approaches 0, such that the product of a and tau are constant, then the response will be finite. This particular case is rather important because it approximates the application for when the driving force is a spike at t equals t sub naught. Expanding x sub I by letting tau approach 0, but with b equal to a tau, yields the following equation. And this equation looks ugly. However, we can apply the Taylor expansion to give an approximate solution. Since tau is small, by the way, this is only for when t is greater than t sub naught. Moving on, since tau is small, one can use a Taylor expansion to approximate the values for e to the beta tau, cosine omega tau, and sine omega tau, and by taking the first two terms, we yield the following. And rewriting this equation in terms of b and omega 1, we obtain this solution, which is exactly the same as this one. And given that the response of the linear oscillators to an impulsive driving force can be represented in such a simple manner, this leads to an introduction of a useful technique known as the Green's method. This method is based on writing the arbitrary force function as a sum of the superposition of the impulse functions. And this is the depiction of how Green's method works. We can approximate this line by the sum of many impulse functions. Using Green's method, one can write the driven harmonic oscillator as a series of impulse functions I sub n, writing it in this manner, where I sub n of t is a piecewise function, where it is a function of t of n and t of n plus 1, and is equal to a sub n of t of n between the intervals t of n plus 1 and t of n, and otherwise 0. The interval of time which I sub n acts is tau, equal to t sub n plus 1 minus t sub n, and since tau is much smaller than 2 pi over omega 1, then the solution for the nth impulse is the following. At t greater than t sub n plus tau, and the solution for all impulses up to the capital nth term is as follows. For t sub capital M, from the interval of t of capital M, n, and t of n. If one allows the interval tau to approach 0 and write t sub n as a continuous interval t prime, then the sum can become an integral, and it has the following expression. And since we define the Green's function to be a piecewise function, to be this at t greater or equal to t prime and 0 at t less than t prime, and since the mass times acceleration is equal to the force, then we have the displacement is equivalent to the integral from t to minus infinity to t of the force at the continuous time interval of the Green's function of the time and the time interval of the continuous time interval, where g of t is the Green's function. And this marks the end of this lecture. Hopefully you learned something about driven harmonic oscillators, and subscribe to learn more about physics.